Let's review a few exponent rules using integer exponents. So I have 3 listed here. What happens if you're multiplying x's to different powers or dividing them, or if you're raising x to a power to another power? To justify these, I'm going to use a couple of examples, like starting with this first one here, x to the m times x to the n. This is like saying, well, what's x cubed times x squared? The rule says that you can just add the exponents, which gives you x to the 5th. The reason this is true is because x cubed means multiply x by itself 3 times. So this first thing here is the definition of x cubed. After that, we have the definition of x squared, which means just place 2 more. And in total, we have 5. So in general, the rule says in this type of expression, you can add the exponents together. And essentially, we're going to use this as a shortcut. So here's one rule. Now, here we're multiplying, but you could also divide x's to powers. So what happens in this case? So I'm going to state what the rule is. When dividing, you would subtract the exponents. But I'd like to justify why this is true. And I think I'll use the same example as I did last time, where, well, what if you had x cubed divided by x squared? X cubed means x times x times x. X squared means just x times x. And these are factors that you can cancel between the numerator and the denominator. So I could cancel this one with that one, this one with this one, and all that we have left over in the top is just a single x. I don't need to write the denominator because I completely canceled everything. And that's x to the power of 1, which is just 3 minus 2. The last rule we have here, x to the m to the nth power, is multiply the 2 exponents together. And perhaps just a quick justification of this. If you had, let's say, x cubed squared, by definition, if you square something, that means you write it out twice. So we have x cubed times x cubed. But that just takes us back to this previous rule here, where I have an x cubed times an x cubed, and I can now add those 2 exponents to give me x to the 6th. So these rules are just shortcuts using the definition. Instead of like doing this middle step every single time, why not just multiply those 2 exponents together to get to the 6? So now that we've kind of lightly justified these, let's check out example 1. So I want to simplify, starting with this one here, x to the 5th to the 4th times 5x to the 8th. To simplify this, I'm first going to deal with x to the 5th to the 4th. And this is exactly what's happening in this rule here. So I get x to the 5th to the 4th is x to the 20th. And then I copy down the 5 times x to the 8th. Now this part's looking different because there's this 5 sitting here, but these 3 things are being multiplied together. I can write those in any order that I'd like. So I'm going to do 5 times x to the 20th times x to the 8th. So written this way, 5 doesn't get combined with anything. I can just copy that down. But I do have x to the 20th times x to the 8th. This looks exactly like this, so I can simply add those 2 exponents together, which gives me x to the 28th. And that's the final answer for that first part. Now let's check this out in the second part of this example. Here we're dividing, so I see the variable y. It's kind of set up like what's happening here, even though it's x's, it means the same thing. I'm going to first deal with 25 divided by 5. I know that's just 5. But the other piece I have is y to the power of 52 divided by y to the power of 7. Since I'm dividing those 2 together, I can simply subtract those 2 exponents. So I'll put that in here as, that's 52 minus 7. If I record that as one number, that's 5 times y to the power of 45. It is completely simplified, and that is the answer to the second part. So in the previous examples, we did have integer exponents, but they were all positive numbers. What if you had a negative exponent? So again, I'm going to write down what the rule is. In fact, I stated this up here. If you encounter a negative exponent, what that is going to do is interchange the location from a numerator to a denominator. So the rule is x to the negative n is equal to 1 over x to the positive n. To justify this one, we can look at something like, well, what is x to the second over x to the fifth? According to the rule that we had on the previous page, we would subtract these two exponents, which is x to the 2 minus 5, subtracting from the numerator to the denominator. And that's equal to, well, 2 minus 5 is negative 3. But likewise, x squared is x times x, and x to the fifth is x times x times x times x times x. If we cancel, we're left with a 1 over x cubed. So the reason behind a negative exponent is just a way to say that if you have an expression and you simplify it, the x's are really left over in the denominator. So x to the negative 3 really means there are 3 x's within the denominator of the fraction. I'm going to incorporate one extra rule here too. That is, if you had 1 over x to the negative n, this is equal to x to the n in the numerator. So a negative exponent just moves things from the top to the bottom, or the bottom to the top. Let's check this out in example 2. All right, I have 2 times x to the negative fifth power. I want to write my answer without using a negative exponent. Now this negative 5, it's attached to the x, but it's not attached to the 2 because there's no parentheses around it. What this means is x to the negative fifth should really be in a denominator. The answer is 2 over x to the positive fifth. This notation is our way of saying, like, okay, that x to the negative fifth just moves to the bottom like this. But what if that negative 5 also applied to this 2 as well, like you put some parentheses around it? Okay, now both of those things are moving to the denominator. Not just the 2, but the x as well. And what's left over in the top is just a 1. So all I did here was note that, okay, I have something to a negative exponent. That means just place it in the denominator. Of course, you could multiply this out further, but again, I just want to get this idea across of what to do if you see a negative power. And in this very last piece, okay, I have 9 divided by 3 times x to the negative fourth. One way you could start is by saying, okay, this negative 4, it's not attached to the 3, it's only attached to the x. I now have something that looks like this. I can take the part in the denominator and move it up to the numerator. So I'm going to take this and I'm going to rewrite it up here so it's directly next to the 9. That is, we get 9 times x to the positive fourth over 3. The exponent is positive. It is no longer in the denominator. The last thing to do is to say, well, okay, 3 goes into itself once. It goes into 9 3 times. And this is a final answer of 3 times x to the fourth. For our last example, I placed a couple of more rules up here which are very intuitive, so I'm not going to prove them. I'm just going to apply them within example 3. The idea here is, if you're squaring something, but there's several terms inside the parentheses, the exponent out here goes to the exponent of everything inside of the parentheses as well. So like up here we have x, y to the n. That n gets applied to both the x and the y as well. Here's what that looks like. I'm going to rewrite this as 3 to the first, x to the fourth, y to the negative 2. So all I did was just put an exponent of 1 on the 3. I did that because this 2 gets multiplied to the 1, the 4, and the negative 2. this is 3 squared x to the 8th y to the negative 4. So continuing, 3 squared is 9. I have x to the 8th, and now I have this y to a negative exponent. And as we talked in the previous example, all that means is the y moves to the denominator with a positive 4. And this is the final answer to that first part. So this idea of distributing an exponent applies within fractions as well. So let's look at this one here. Same idea, this 2, it's going to get multiplied to every single exponent. Let's see what we get. Okay, I have x to the 10th, y to the negative 6, divided by, okay, I get x to the 14th, and then y to the negative 4. All right. Next, I think what I'm going to do is make all of the exponents positive. That means this piece is going to go up to the numerator, and then this thing is going to drop down to the denominator. We have 2 negative exponents. They're both going to switch locations between numerator and denominator. And nothing is going to happen to the x's. Okay, let's see what we get. I have x to the 10th, but now I have a y to the positive 4th. I'm dividing by, okay, nothing happens to x to the 14th, but y to the 6 moves down to the denominator. All right, next, I can subtract these two values and these two values since the x's and the y's are the same. So we have x to the 10 minus 14, which is negative 4. We have y to the 4 minus 6, which is negative 2. And as my last step, to make those exponents positive, I'm going to place them back into the denominator. That means I have a 1 on the top, I have an x to the 4th over a y squared, and that is the final answer to this problem.